Hi, Geometry. This is Unit 2, Lesson 13, page 281. And I'm doing a notice and wonder about diagonals. But we already discussed this information in Lesson 12. So I want to remind you what we learned in Lesson 12 about the diagonals. In a parallelogram, my diagonals bisect each other. So obviously DB is shorter than AC. So my diagonals aren't the same length, but what they are is bisected, split in half. So my two halves are congruent. In a rectangle, yes, my diagonals bisect each other, but going a step further, in a rectangle, my diagonals are congruent. So EG and HF would be exactly the same length, my diagonals. So if you could turn your books to page 282, 13.2, your book breaks this particular proof down into 4 parts. The conjecture is that the diagonals of a parallelogram bisect each other. And through drawing a sketch, writing convincing arguments, figuring out the necessary needed information, ultimately, you're going to prove that the diagonals are bisected. So we're going to do all of that work, but we're going to go ahead and do it on our first page. So going back to page 281, let's set this up. So activity 13.2 from page 282, the conjecture was to prove the diagonals of a parallelogram bisect each other. And we're going to be given a parallelogram ABCD. I'm going to choose to use the one that's up above on your page because that'll keep, so you're not accidentally looking at the wrong parallelogram. We're going to keep the same letters in the same order and everything. So why don't we sketch this parallelogram? Since I've already marked my diagonals congruent, I can't use that one. That's what I'm trying to prove. I actually don't know that information yet. So I'm going to redraw the parallelogram, and I'm going to call it A, B, C, D, and let's draw in our diagonal AC. Let's draw in our diagonal BC. Let's have both diagonals intersect at X. And then what I'm trying to prove is that the diagonals are bisected. So I'm trying to prove that AC and CX, using corresponding parts, are congruent. I'm trying to prove that BX and its other half, DX, are congruent. Now to do this is the first time when we do our proof that I'm not going to use the entire triangle made by a diagonal. Instead, I'm going to use 2 of the 4 little triangles you now see. I can do this proof either using the top and bottom or the 2 sides. So it matches the notes in the locker. I'm going to use the top, or I guess we're calling them in folders now. I'm going to use the top triangle and the bottom triangle to prove this. So I'm going to show these 2 blue triangles are congruent. If these 2 blue triangles are congruent, then DX and BX would be corresponding parts of 2 congruent triangles, so they'd be congruent. And AX and CX would be corresponding parts of 2 congruent triangles, so they'd be congruent, and I prove this. So let's get started. My statements, so far, the only statement I have is that I have a parallelogram. So I've got parallelogram ABCD. And that would be the reason is my given. So what sort of stuff do I know? So I need 3 things to prove my 2 triangles congruent. I need either side, 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 or angle, side, angle. So let's talk about the things I know because it's a parallelogram. So first of all, if it's a parallelogram, I know that opposite sides are parallel. Also, if it's a parallelogram, I've proven in lesson 7 that opposite sides are congruent. So I do have this top side and this bottom side congruent to each other. If these 2 sides are parallel, then I have alternate interior angles. So this is where this proof that I'm going to do with you, I'm going to set it up to use angle, angle, side, because we haven't done that very much. I think it's only been in one other proof maybe, but this could be an angle, side, angle proof as well if you use both sets of alternate interior angles. But I'm only going to use using the top and using DB and the bottom. I'm going to call this angle 1 and I'm going to call this angle 2. I'm just going to use one pair of alternate interior angles. So notice that I'm not marking this pair and I'm not going to use them because I'd like to use angle, angle side in this proof. So this is 1 up here. If it's gotten kind of messy, that's angle 1 and this is angle 2. I've named them that way so I don't have to name them with 3 letters. Okay, so the other angle that I know is congruent is my vertical angles. We haven't used those in a little while, so let's use my vertical angles there. This is where I'm getting angle, angle, and my non-included side. Angle, angle, and my non-included side. So I'm going to prove these two triangles are congruent with AAS. You could write SAA. It's just that the books tend to write AAS. So again, you had another option. If you did these two angles, you could do angle, side, angle. Okay, so let's get started then. I marked 3 different things on here, and I got to get all 3 of those things in my proof. So the first thing I marked is that I marked my parallel lines. That's the definition of a parallelogram. So let's write that down. So my top and my bottom are parallel. So I know AB is parallel to CD, keeping corresponding parts in the same order, but I don't think you have to for that. But that's the definition of a parallelogram. And then based on that, I got my 2 alternate interior angles. So let's go ahead and include those for right now. Because my parallel sides, that's why angle 1 is congruent to angle 2. And you could name them with the letters if you wanted to instead. And that's because alternate interior angles are congruent. I also said that my opposite sides are congruent because it's a parallelogram. So let's get that in there. So now I'm going to say DC congruent to, I'm going to say BA, keeping corresponding parts in the same spot. And that's because opposite sides of a parallelogram are congruent. And remember, you have an entire proof for this. I forget what page it is now, but that was in lesson 7 of our book, our workbook. So now let me double check what I've got here. I've got my alternate interior angle, that's one of my A's. I've got my opposite sides, that's my S. Oh, I don't have my vertical angles on here yet. I don't have my third thing. So my vertical angle, I could name these any way I want. I'm going to name it DXC on top. So then for the bottom, I need to name it BXA, getting my corresponding parts in the same position. And that's because vertical angles are congruent. So now you'll notice I have all 3 parts of my angle, angle, side. So now I can say that the triangle on top is congruent to the triangle on the bottom. It's going to be by angle, angle, side. When I name the triangle on top, I can put it in any order I want. I'm going to go ahead and just use the same order I did for the angle. I'm going to call it triangle DXC. So that's going to be my triangle on top. And that would be congruent on the bottom to BXA, that triangle. And so now, if these 2 triangles are congruent, I know all the other parts, where there's 6 corresponding parts, and I've got 3 congruent to 3. So now all the others are congruent. I now know this side is congruent to this side by CPCTC. I now know this side is corresponding to this one, so they're congruent by CPCTC. And conveniently, those are the sides I'm trying to prove. Those are the different bisected halves of the diagonal. So I'm going to end this by writing what I'm trying to prove, AX congruent to CX and BX congruent to DX. and that's simply because of CPCTC. And I have proven that the diagonals of a parallelogram bisect each other. All my conjectures are provable about my quadrilaterals and parallelograms. So let's take a look. So that was all of 8.2, the next 2 pages. So let's take a look at page 285. This should have been done in Zoom. So at this point, if you're coming to this video from Zoom, you could probably skip this page. But in this page, we're going to talk about what's special about these quadrilaterals and diagonals. So they're saying that you have 2 intersecting segments, which always make a quadrilateral if you connect the endpoints. What's true about these intersecting segments? These intersecting segments are the diagonals. So let me show you what they're describing with the rectangle. For instance, in a rectangle, if I have 2 intersecting segments that are exactly the same length, I don't think I did my sketch very well, but if I connect the endpoints of those segments, I have a rectangle. Remember, the diagonals are congruent for a rectangle. We just talked about that on the other page, and we talked about that in lesson 12. So what about a rhombus? You need to remember what we learned about a rhombus in lesson 12. That is that my diagonals are perpendicular to each other. You can draw these intersecting segments any length you want, but they should look like they are intersecting. Well, actually, I just also made right angles, so this isn't a very good sketch for a rhombus. Sorry. So they can't be congruent, but they need to be perpendicular. And when I draw diagonals that are not congruent, but that are perpendicular to each other, then my sketch comes out to be a rhombus. Remember, that's my 4 congruent sides. So this is when my diagonals are simply perpendicular. So now a square are both of these things. My diagonals for a square, that's what I started drawing here, they should be perpendicular, but they also should be exactly the same length. They should be congruent, just like a rectangle is. And then when I connect my endpoints, the sketch that I'm getting is a sketch of a square. How about a kite? Well, interestingly enough, in a kite, my diagonals are also perpendicular. Remember, a kite is really a reflection over the longer diagonal. So I have a short diagonal and I have a longer diagonal. And when I connect my points, I should have my 2 consecutive sides congruent. Remember, that's what was special about a kite. So in this kite, my diagonals are perpendicular as well. And an isosceles trapezoid. Well, let's remember an isosceles trapezoid. Well, an isosceles trapezoid, those diagonals should be congruent to each other, so the same length, but they don't bisect each other. This is not a parallelogram, just like a kite is not a parallelogram. So this guy is not drawn very well, sorry. But my diagonals should be exactly the same length, so my diagonals are congruent. But they do not bisect because this is not a parallelogram. Same thing with kite. My diagonals are perpendicular, but they do not bisect because a kite is not a parallelogram. And I believe you guys worked on those in Zoom. So if you were absent, that's one of the things that students did. This page, it discusses further that the diagonals bisect each other, the statement and also the converse. So let's take a look in the practice. I'm going to actually put 1 and 2 together. So this is the practice for Unit 2, Lesson 13's practice. And numbers 1 and 2 I want to put together. It's a proof. So the top, you're drawing a diagram of a situation you already have in number 2. You're marking given information that we can mark on the diagram in number 2, and you are restating this conjecture more specifically for this diagram in number 2. So we'll just do everything about number 1. We'll do it down here on top of 2. So number 1 says a quadrilateral with one pair of sides both congruent and parallel is a parallelogram. So I have a four-sided figure, and what I'm given is that one pair of sides is both congruent and parallel. What I'm trying to prove is that it's a parallelogram. So let's look at this guy. This guy is a quadrilateral, and it's going to have AD congruent to BC. Let's mark that. That's my one pair of congruent sides from number one, and AD is parallel to BC. So that's my congruent side also being parallel. And I'm supposed to show that ABCD is a parallelogram. So this is similar to a proof we did earlier in a lesson where we used converse of alternate interior angles are congruent. So I'm going to do that again with this proof. We're going to get it started, and you're going to finish it and bring it to Zoom. So this also, I'm going to put number 1 and 2, so it's really the same thing. So in number 1, we're going to be given the following information, that AD is congruent to BC, and we're also given that AD is parallel to BC. So in this problem, it says restate the conjecture as a specific statement using the diagram. So in this statement, we're going to say if AD is congruent to BC and AD is parallel to BC, then ABCD is a parallelogram. So that's taking what it said above and making it very specific for the drawing I have below. So then what I'm trying to prove then is that this is a parallelogram. So I'm trying to prove that ABCD is a parallelogram. So let's take a look at how I might get started. So I'm trying to think of the things I know that aren't currently marked. I would like to get these two triangles congruent to each other. If I could get these two triangles congruent to each other, then I maybe could get the top and the bottom parallel, because if the top and the bottom are parallel, then I could use my converse of alternate interior angles are congruent to show, I could use this to show the top and the bottom parallel. And if my top and bottom are also parallel, then I could use the definition of a parallelogram because I would have both pairs of opposite sides parallel. So let's get started and think about what we know. Well, this side is reflexive. Okay, I can mark that. And let's try to use the fact that my sides are parallel. So if I use my sides are parallel, then if I make a Z with my transversal and my sides are what's parallel, I know that this angle and this angle are congruent. I'm going to call it angles 1 and 2 for ease of my proof. So I can prove these two triangles congruent by side, angle, side. Great. I don't know. And then I'll worry when I get done with that, I'll worry about proving that the top and the bottom are parallel to each other. So let's first of all prove that the two triangles are congruent. So my first statement is going to be what I have given is that AD is congruent to BC and AD is parallel to BC. So that was my given. So now my statement 2 needs to be either I'm going to talk about my alternate interior angles, or I can talk about my reflexive side. That doesn't matter which one I do first. I'm going to do my reflexive side. So now I need to think about, is this a twist or is this a reflection with no twist? So this is a twist because 1 twists down here to 2. So when I write this, I've got to write this as CA. So then that is the reflexive property. So I've got 2 parts of my statement. I remember I'm using side angle side for this, side angle side, side angle side. So I've got a side, I've got my other side. What I don't have in here are my angles yet. So let's get my angles in here. I called it angle 1 congruent to angle 2 to make it easy to name. And that's because I have alternate interior angles congruent. So now I can say my two triangles are congruent. I can name them however I want the first time, and then the second time I have to match. So let's call it, what would you like to call it? DAC. So DAC is congruent to BCA, and great. So now wait a second, I want to get my top and bottom parallel. So just a moment, if you look at this, remember now I know all the other parts of my two triangles are congruent by CPCTC. So think with me for a moment, if this top part was my Z, and if this transversal, and if this bottom part was my Z, if I could get this angle congruent to this one, oh, well, there you go. If I could get that angle congruent to that one, we'll call it 3 and 4, then those would be the alternate interior angles for the top and the bottom. I could then prove the top and the bottom are parallel. So let's work on getting 3 and 4 congruent. So I know that angle 3 is congruent to angle 4 because those two angles are corresponding parts of two congruent triangles, so they have to be congruent. And if 3 is congruent to 4, those would be the alternate interior angles for these two lines. They would have to make AB parallel to DC. So I know that AD has to be parallel to, what would that be? Oh, I'm sorry, I said that wrong. It's AB, my top. Sorry about that. So AB, and then I would have to say CD, getting them the corresponding parts. Those two are congruent because of the converse of alternate interior angles are congruent. The converse is if I know the angles, I can then say the lines are parallel. And I'm basically done. I have in my given my sides parallel. I have now stated that my top and bottom are parallel. So I know that this is a parallelogram by definition. So ABCD is a parallelogram. And that is definition of a parallelogram. Going to the rest of the practice, I wanted to mention on this particular problem that this is basically the proof you and I did, that the diagonals of a parallelogram bisect each other. So when you're looking at these choices, I believe 2 of them work. But when you're looking at these choices, remember, we proved it using the triangle on top and the triangle on the bottom. Very similarly, you could also prove this, but we didn't. But you could prove it using the triangle on the side and the triangle on the side. What we did not do was prove it using the entire triangle on top and the entire triangle on the bottom, for instance. So think about what triangles you're using to prove your sides are congruent. Will help you with one of these statements that you're supposed to select. And also on number 5, I wanted to give a little hint on this one. Notice that the right angle marks, so these are right triangles. You do have a congruence theorem that you could use only with right triangles. You might think about getting the correct parts to be able to use that congruence theorem for number 5. Thank you very much. See you in Zoom.